And the way you get that value is by multiplying first component to the first component, second, third, and so on, you add them. Alternatively, it can be proved that this dot product of two vectors is given also by this quantity, length of u times length of b, these are two numbers, times cosine of the angle between these two vectors, between vector u and v. Well, for this course, you don't need to know cosine of some angles. We will only work when we have the cosine of theta is given, or you can use the other way. Only the cosine of theta will be asked. So it is given by these two formulas. And before I go do some examples, I want to just add some notes here. That first, dot product of two vectors is a number or a scalar. So dot product of two vectors, any two vectors, is scalar. It's a number, it's not a vector. And it can be done for vectors with two components, vectors, three components, vectors in n components. The way it's done is very similar to what we see here. The only thing matters is that they have the equal number of components. So this is dot product is defined for any vectors, any two vectors with the same number of components. And it works like that. The last note is very important for us, and it is that, okay, I can take this formula and I can rearrange it and find a formula for cosine theta. This formula is something that you need to know. Cosine of the angle between two given vectors is given, you see, u dot v is here, and I divide length of u times length of v to the other side. So this is u and v. Okay. This way, you can, this cosine formula, you can use this formula if you know the components of the vector, use it and find the angle between these two vectors or any given pair of vectors. I will start doing some example. Let me just fix two vectors. Let u be 1, -2, 3, and v be 2, 0, 2, two vectors. Then we can find u dot v. U dot v is, while you multiply first component to the first one, 1 times 2, negative times 2, 0, 3 times 2, and then add them. Here in this case, this is 2 plus 0 plus 6, which gives me 8. Also, I can ask for find the cosine of the angle between u and v. Well, this means that, okay, I don't know what is the angle, but I can find cosine of theta. It is given this way. You have to put u dot v, it's a number in the numerator, find the length of u, length of b, and divide it, put it in the denominator. So in this case, we already found u dot b, it is 8. Length of u, remember, to find the length, we square each component. And then add them and find the square root. That's length of u. Length of b is 2 squared, 0 squared, 2 squared. This will give me 8. Root of, this is 1 plus 4 plus 9, it's root 14. And this guy is 2 squared is 4, 0, 4. And that's the level that you have to be able to work with. There are different simplifications that you can be asked here to do. For example, here I'll just make sure that I wanted to make sure that you understand some of these calculations. You see, 8, you can write it as root 8 times root 8. And then you can cancel this with that. Then this is the same thing as root of 8 over 14, and that is 4 over 7. Well, I can go a little bit further. Root 4 over root 7. Root 4 is 2 over root 7. Wow. Any of these ones, you have to be able to turn one to the other one when you're doing calculations. So most of the time, this will be what you need to understand. But if there are questions in which the course, the question designer have got one of the other options, you have to be able to turn it to that. Any questions, any comments before I go to another example? Let me write down another example and ask you to complete this one. How about we take a vector, let u be 1, negative 1, 0. Length of v is given is 2. Find the cosine of the angle between u and v if we know that u dot v is 3. So I'll give you maybe 30 seconds to work on this example. The formula you need here is the cosine formula, which is posted up there. Please go ahead and try to do this one and give me the answer. Can you find the cosine of the angle between these two vectors, u and v, with these information given? And I need a number there. If someone finds it, please post it there on the chat. Okay, any answer? Any values there?
It would be 3 over 2 times the square root of 2.
Thank you. This was Rachel, yes?
Yep.
Thank you, Rachel. So this is the formula, yes? So u dot v, length u, length v. So in this case, u dot v is given 3. Length of u, we can compute ourselves. This is negative 1 squared, 1 squared, 0 squared. Length of v is given, it is 2. So this will be 3 over 2. And then 1 squared is 1, negative 1 squared is 1, 0. So add them, you get root 2. So I multiply 2 to root 2. That's the number that Richard gave me. Thank you. When we work with dot product, there is a very important case that dot product can detect. And this is when we have two vectors, which are called orthogonal vectors. Two vectors are orthogonal if the angle between them is 90 degrees. In other words, while this is what we call perpendicular in the other settings, but for the vectors, the terminology we will use is orthogonal. The angles between two vectors are 90 degrees. It's called orthogonal. Well, finding orthogonality relationship is important. But if you know one small fact about the trigonometric ratios, that cosine of 90 degree is 0. And that gives us very important test. I'll call it orthogonality test. Well, it says that two vectors are orthogonal. There's u and v are orthogonal if and only if their dot product is 0. So if the angle between them is 90 degrees, look at this guy here. This is going to be 0, and 0 times anything else is 0. So that's how you know at least one side. If they're orthogonal, u dot v is going to be 0. The other way around is also true, meaning that if dot product is 0, then the vectors are orthogonal. And this is very key and very important for us because we will use this kind of this test to check the orthogonality of two vectors. Without this test, it's very difficult to check, to find it. But just by this, you can just do dot product and get if two vectors, given vectors, are orthogonal or not. So let me just write one example here. This is a question. Are vectors u, which is 2i minus k, and v, which is k minus I plus j, are these guys orthogonal? Okay. First thing, well, orthogonality test says that, okay, find the dot product. What is the dot product of these two guys? So u dot v, we want to find that. But for that, I need components of these vectors. These are given in ijk notation. Remember that coefficient of I is the first component, coefficient of j is the second component, and coefficient of k is the third component. So this is the same thing as writing this guy, that, and that for our vector. So in this case, the coefficient for u, coefficient of I is 2. Coefficient of j, there's no j in u, so that means that this is 0 and negative 1. Dot coefficient of components of v, 1, negative 1, and 1. And then you dot product 2 times 1 plus 0 times negative 1 plus negative 1 times 1. And then we see this is 2 plus 0 minus 1. This is 1. It's not 0. So that means that 2i minus k is not orthogonal to v, which is k, I, and j. There will be questions or cases that you have to try to find some values for which the vectors are orthogonal. So this is an example of that form. It says that find the value or values of k for which these two vectors, k1, 2k, and v, which is k minus 1, 4, and 3, are orthogonal. So these are two vectors. They each of them has three components: 1, 2, 3, 1, 2, 3. But in the components, we have a variable unknown k, and the question is asking to find values of k for which u and v are orthogonal. In other words, we have to see for what values of k the dot product of these two guys is 0. This is another way of writing this. So for what values of k, u dot v is equal to 0. This is equivalent way of rephrasing that for you. But why is it important? Because we can find dot product now for these two vectors. K times k minus 1, this is first component times first component. 1 times k, 4, and 2k times 3. This must be equal to 0. And from there, you see that k squared, I expand this, minus k plus 4 plus 6k must be equal to 0. In other words, k squared plus 5k plus 4 must be equal to 0. Now I have to solve this one. What are the values of k which makes this one 0? Can anyone solve this equation or tell me how you can solve this equation?
You can factor it.
You can factor it, or yes, you can use, if you don't remember this one, you can check it again. So you can use the quadratic formula as well. But this case, it's easy, as Rachel said. So we have two values of two numbers. When you add up, you get 5. When you multiply, you get 4. So that's plus 1 plus 4. And from there, you get either this one is 0 or that one is 0. And from that, it means that k either must be -1 or k must be -4. And those are the values that makes these two vectors orthogonal. So k, -1 and -4 for k, the vectors u and v are orthogonal. This way, you find that those values of k. So you know that orthogonality can be expressed in terms of dot product. That dot product must be equal to 0. You express it, that will give you an equation. You solve that equation, and you find the values or solutions of that question. Definition of dot product, cosine formula, orthogonality. These are three important things that you need to know for the dot product. Any questions, any comments? I will move to the next part, which is cross product of two vectors. Okay, so then let's just start. First, the definition. Cross product, first thing to remember, cross product works only for vectors in R3. So the cross product of two vectors. So let me fix them. U, which is U1, U2, U3, and V, which is V1, V2, and V3 in R3. Well, you already see there it has, both of them have three components, but I want to emphasize that dot product, cross product is defined only for two vectors from R3 with three components. So cross product of this guy, first of all, is a vector in R3 again. So cross product, the result of cross product is a vector again. And we denoted by U, well, cross V. For dot product, we put dot. For cross product, we put cross. The notation is important, but even more important thing is that how do you get those components? Here, the result is going to be three. Result is going to have three components. I have to tell you how to compute the first component, second component, and third component. The way it works is this. The first one is U1, U2, U3. You put it in the first row. The second one, you put it in the second. The order matters here. So you have to do that one. And then here's what you do. For the first component, you cover the first column. The remaining is 2 by 2. It is, we call it matrix. So you just put the remaining ones in a 2 by 2 form. And then, well, let us just write that. This is determinant, and we find the determinant of that 2 by 2 remaining one. Minus, for the second one, you cover the second column. The remainings are form 2 by 2 matrix. And we need to find the determinant of that and then multiply by negative. This is for second component. It's important to leave that negative sign on there. And then for the last one, you cover the third column. The remaining is U1, U2, V1, V2, and then find the determinant. This is the formula. You may know different formulas, but I suggest that make sure to learn this one. This is something that we will get back to and do a little bit more work with this in chapter 4. You may say that what is the determinant of 2 by 2 matrix? This is an easy determinant, A, B, C, D. What you do, you first multiply entries on the main diagonal. This is called main diagonal, A, D, and then multiply entries on of diagonal, so BC, then subtract AD minus BC. Okay, so this way, cross product, the components are given this way. So you multiply U2 to V3 minus V2 U3. There's a negative sign there. I just bring it down. U1 V3 minus U3 V1. And the last one is U1 V2 minus U2 V1. This way you find the components, and that's how cross product works. Let me just do an example here before we go, and you see how this whole thing works in practice. So find find 1, negative 2, 3 cross 2, 0, 2. Okay, so I do 1 minus 2, 3, 2, 0, 2. The first column, you cover the first column. The remaining is negative 2, 3, 0, 2. Find the determinant of that. Then you cover the second column. For second column, you should remember there's this extra negative sign. And what you do is you cover second column and then determinant of the remaining 2 by 2 matrix. For the third one, again, we're going to find determinant of 2 by 2 matrix, but this is the 2 by 2 matrix we obtain by deleting the third column or covering the third column, and that is 1, negative 2, 2, 0. Okay, determinant of 2 by 2 matrices is, do you multiply diagonal entries, these guys, negative 2 times 2 minus off diagonal entries, minus 1 times 2 minus 3 times 2. Then 1 times 0 minus 2 times negative 2. So this way I have the first component, negative 4. I have the second component, this is C, 2 minus 6 is negative 4 times another negative sign is 4. And negative 2 times negative 2 is 4. Negative 4, 4, and 4. That's what we have for cross product. Any questions, any comments before I move on? Before we go further, let me just write a few remarks here. One is that, well, I already mentioned these ones, but this is important. It's good to have it somewhere. First thing is that cross product is only defined for vectors with 3 components. So cross product is defined for vectors in R3 only. So we don't have cross product of a vector with 4 components cross another vector with 4 components. Compare this one with the dot product, which you can do dot product of any 2 vectors with the same number of components. Cross product, the result of the cross product is a 3-component vector. It's a vector in R3. And, well, compared to dot product, which was just a scalar. And out of all the properties that the dot product and cross product have, there is one very important property for cross product, and it is that cross product, the order in the cross product matters. So if you switch the cross product order, you may get differently. In dot product, the order doesn't matter. You multiply u dot v, you get the same thing as v dot u. But for the cross product, the order matters in cross product. In other words, we have more precise description of what will happen. If you switch the order, so you do this v cross u, the result will be negative of all you have. So examples for this is, well, for cross product in general, is that you see we found one do you see the example that I did before? It's the result is negative 4, 4, and 4. Now, if I switch the order, the result I will get, this is a good practice, do it yourself here. If you do that, you will see that you're getting 4, negative 4, and negative 4. That's very important property that you should keep in mind and know that what is happening there. Let me write another example and try to see if you can do this one. Compute this cross product, 2i plus j cross k minus I plus j. Okay, go ahead, please try to do this one. I'll give you 30 seconds. Any results there for me? Well, I'll turn this one to the component notation. 2, 1, and 0 cross negative 1, 1, and 1. These are the component version of these vectors, which are given in IJK notation. And this will give me the determinant of 2, 1, 0, negative 1, 1. I cover first column, I get 1, 0, 1, 1. The second column, I get 2, 0, negative 1, 1. And I cover the third one, I get 2, 1, negative 1. And this gives me 1 times 1 minus 0 times 1. 2 times 1 minus 0 times negative 1. 2 times 1 minus 1 times negative. This is 1. This is negative 2. And the last one is 3. So the result is I minus 2j plus 3k. That is the cross product of these two vectors given here. Any questions, any comments? Okay, so now we learn how to do work with the cross product and compute cross product. But we want to know what is the length and what is the direction of a cross product. So we want to learn about more geometric meaning of this cross product. Length of U cross V, and what is direction of U cross V. These are interesting facts here, which we will use very soon, both of them. One is that the length of cross product U cross V. So it is a vector, so you can find the length. What is this length? This length is actually equal to the area of the parallelogram defined by U and V. So in other words, when you have two vectors in R3, these two vectors, they form this very interesting, nice parallelogram, yes, in the same plane, and you can find the area of that. Area of this parallelogram, this is U, this is V. The area is given by U cross V. This is a vector. You find the length of that. That's going to be the area. How about the direction of the cross product? This is U cross V. Sorry, change this. U cross V is a vector orthogonal to both U and V. In other words, when you have this U and V, U cross V is a vector which is perpendicular to both of them. Its length is given by area, but its direction is perpendicular. There is an interesting way of, they call it the right hand trick. So it goes from UV when you put your fingers in the direction of U, and so that when you close it, you get to V. Your thumb shows the direction of U cross V. For you, this is the important thing. The length of U cross V is the area of parallelogram formed by U and V, and the direction of U cross V, it's a vector which is perpendicular to this vector V. So this is both U and V. So this is U cross. Usually, you see, now we can compute these things. So it means that I can use this one to find the area of parallelogram formed by two vectors. For example, before I go to example, is there any questions, any comments? Okay, find the area of the parallelogram defined or formed by 1, -2, 3, and 2, 0, 2. Well, we know that the area of this parallelogram is given by length of u. It really doesn't matter which one you take, u and v here. The cross product will be different thing, but when you take the length of that, it's going to give you the right value. So if you change the order, the cross product will be different, but the length will be the same. So this means that I have to find the cross product of these two vectors. We already computed this guy actually up there here. -4, 4, and 4. So -4, 4, and 4. And this is -4 squared, 4 squared, and 4 squared. That all together it gives like 16, 16, 16, 48. Other way of writing is 4√3. So the area of this parallelogram, which we don't have any easy way of imagining even this parallelogram, but we can find its area. It is 4 times √3, something close to 7, something like that. But one can go further. Actually, one can go and ask questions like this. Find the area of the triangle formed by these two vectors, say 2i plus j and k minus I plus j. Well, we know that the area of triangle, so look at this triangle for a second. See how does this work? Area of u and v. I don't know what are these guys, but well, when you have two vectors, you can form this triangle. But there is a key point here for you to notice that this triangle is actually half of the parallelogram formed by u and v. So in other words, you see, it's exactly making that parallelogram half. So this will be half of the area of this parallelogram formed by u and v. Why I turn it to parallelogram? Because I know that the area of parallelogram can be computed by finding length of cross product. And then if I divide it by 2, I get the area of the triangle formed by this one. So we already did compute this cross product. So I'll use that fact, that result up here, which is 1, -2, and 3. And this is half of 1 squared, -2 squared, 3 squared, and that's √14 divided by 2. Any questions, any comments here? So I will finish this review by very last formula or last point of this course. This is area of a parallelopiped. When you have 3 vectors in R3, so let's say u, v, and w, you can form this three-dimensional object or box, which is this kind of distorted cubic or rectangular box. This is a rectangular box. You push it a little bit in one direction, and it's just like that. This is called the parallelopipet. Formed or defined by U, V, and W. We have a formula for volume of parallelepiped formed by three vectors, and this is the formula you need to know. So the volume of the parallelepiped defined by U, V, W is. So you pick any two of these vectors. So U cross V. You take any two, doesn't matter. You can take the first one, last one, first one, second one, or last one and second. Doesn't matter. You cross product. This is a vector. Then you can dot product the third vector to the result of that cross product. So this was a vector. I can dot product. I get a vector, a number. This number could be positive or negative. So we want to get always positive number out. That's called absolute value. It means that if it is negative, you just drop the negative sign, make it positive. That is going to define or give you the volume of parallelepiped. So you just take any two of them, cross product, the result you need to dot product with the third one and find absolute value. Let me do an example here. Find the volume of the parallelepiped defined by these two vectors, these three vectors, 1, -2, 3, 2, 0, 2, and 3, -1, 0. We know that the volume is given by, so you take any of these two. I take these two, one. You cross product them. This is a vector, then dot product the first one to that. Then if this number is negative, make it positive. Volume always needs to be positive. So 3, -1, 0, dot. The cross product of this guy, actually, we already did this one in our first example. This is going to be -4, 4, and 4. Now, the result is a vector. The remaining is dot product of two vectors. Here is 3 times -4 plus -1 times 4 plus 0 times 4. The result is -12 minus 4 plus 0. And that is -16. See, without absolute value, we would have got a negative number, but this negative number is not a good number there. Volume cannot be negative. That's why this absolute value is important in this formula. It means that you just drop, absolute value means that drop the negative sign. This will be 16. So the volume of the parallelepiped defined by those guys is given by 16. Okay, so this brings us to the end of what I had prepared. So we went over 1.2, which was about two products, dot product, cross product. Then we learned about how to compute each one of them. Then the formulas, what kind of applications these ones have. For example, for dot product, we had this cosine formula, and we had the orthogonality test. For cross product, we know that the length of the cross product is equal to area of the parallelogram defined by two vectors. And we know that the its length is orthogonal to the vector, to both of these two vectors. The last thing that we did was that we have a formula for the volume of a parallelepiped given by three vectors in R3. Just make sure that you do work on the properties of dot product, cross product, a little bit more. There are in the textbook, there are examples for that. And make sure that you understand all these stuff from chapter 2. So I'll stop recording.